when you have the more water transferred, the impact of irrigation water cost saving is also stronger. Second, let's look at the impact of input use. So when we look at the impact of input use, the three impacts, irrigation water, cropland, and fertilizer, we find that with SNWTP, the use of all three inputs increase for the basins that are receiving water. And similarly, we see the patterns that differ from each other across scenarios and across the baselines by basin. That is due to, first of all, the difference in the amount of water transferred. Second, the difference in the background agricultural water supply. And third, for the different basins, they also have different great specific substitution between these inputs. And when we holding other drivers constant at the same baseline level, we realize that when we have more water, again, the amount of input use will also increase in these water receiving basins. For the water donating basins, again, they will have decrease in the input use, but that the magnitude of that change is much more less than the water receiving basins. First, let's look at the impact of crop output. So at the basin level, we find that the SNWTP increases the amount of crop production in the water receiving basins, but decreases the amount of crop production in the water donating basins. Furthermore, we also see that for all the other basins that are not affected by SNWTP directly, the sum of their crop production change is also negative. This is because that when we have the water SNWTP, the water receiving basins, they have decreased the production cost, which gives them a comparative advantage in crop production. So in China, more crop will be produced in this basin. Also, because in these scenarios, we set the total demand of crop to be fixed by the socio-economic driver. So the increase of crop production in the water receiving basins is related to the decrease of crop production in other basins, no matter they are included in SNWTP or not. So it shows the impact of SNWTP on changing the national pattern of crop production. And similarly, as the input use we see in the second set of results, the impact of SNWTP, it varies across basins, and also it varies with different scenarios now and the future. But in general, the result is consistent that when we have more water transferred, the increase of production will also be higher, which is consistent with our economic intuition in the model structure part. And then let's look at the impact on spatial level. The simple China model also produces the simulated results of crop production on spatial level. From this spatial level, if you look at the map for central China, we also see that even within the same basin, the impact of crop production are different across different regions. That indicates the spatial heterogeneity of natural endowment and input substitution and response to macro shock on the region level. And also on the map of whole China, we see the impact of SNWTP is not only restricted to the water receiving and water donating basins, but also for other regions in China. So, conclusion of this paper is that SNWTP's impact on agriculture is that it reduces the irrigation cost in the water receiving basins. So it encourages to use more input and also to produce more crop in these basins. And as we can see, the impact of SNWTP varies across basins and varies across different scenarios. However, when we have more water transferred, the impact on crop production input use and output will also be higher. And also, we find that the impact of SNWTP is much larger than the water receiving basins, than the water donating basins. It also has slightly effect on the other basins through the market linkage, even if they are not directly involved in SNWTP. And the fourth finding is that we realize that there's a little trade-off between the more cropland, between the more crop production in water receiving basins and the increased use of cropland and fertilizer, because they will have the negative impact on the social economic, on the ecosystem, and may cause all other environmental issues. Finally, from the spatial pattern of SNWTP, we realize that the SNWTP impact it also shows the spatial heterogeneous. So when we are going to planning for policies in order to boost the crop production or control for the environmental issues, we should also pay special attention to the regions that are more sensitive for the impact of SNWTP. So here it shows the reference of this research, and thanks everyone.
Thanks for your interesting presentation and interesting. So, do you have any questions? I don't see anything in the chat. So I have a couple of myself. Has to do with the model. You have used a simple, right? Probably you explain, but how does the model treat?
Martina, I think we cannot hear you clearly for some reason.
Yeah.
It's my fault. That's strange. And now?
Not better.
Okay. So the question is, how does the model treat crop response to change in input factor, especially water supply? Is it modeled within the simple G model?
Yeah. Okay. So thank you for your question. So the simple G China model is a variant of the general simple G model. It has the similar structure as that. For the crop supply system, we use CET function to separate the crop supply into the five different inputs, and each of the linkage we see here refer to a CET function. So when we have the change of one input, both the price change and also the quantity change will affect the aggregated input on the upper layers. And with the C structure, it will eventually influence the crop supply in that grade.
So I think here the key, the CET, so it's quite a traditional use modeling technique in this kind of framework. So we know there will be substitutions between the inputs within each layer, but the trick is how do we treat water? So here we so other inputs like land and nitrogen, those are specific by grid cells. So the competition takes place at grid cells. But the water is a little different because we define different water basins within China. So there were altogether 100 water basins, but there are like a 40, no, like a 80,000 something grid cells altogether in China, but there are only 100 basins. So we're assuming water can flow freely within the river basin. So all the grid cells with cropland within the river basin will compete for the same amount of water at the same time. So that's why we are building this equilibrium, like a water supply and the demand. So the water price will be the same for the same basin. So that's the thing that we created to make this water transfer convenient, because those transfer projects largely won't be limited by the grid cells, so will be limited by basins instead.
Okay.
Yeah, I would like, thank you, Sam, for a nice presentation. I would like to know more about the energy implications of the water transfers. Could you please elaborate on that?
Excuse me, so you mean the implication on energy?
Yes.
Okay, yeah. So basically, the purpose of the SNWTP is to fulfill the water demand in the northern China, including both the commercial use and also for the industrial use. So basically, we see that the water transfer project itself is to move water from the south to north. So itself will take the energy and also for the considerable budget. And maybe we can try to see if it can balance the energy use with, and also how will that influence the industrial impact in northern China, because the different industrial sectors, they have to use the water, energy, and other input of people. I'm not sure if I understand your question right.
Let me say another words about this. So a big background. I like the question, Alvaro. So it's very relevant because the project was actually out of a big project funded between China and the U.S. and SF. And then the theme of the project was the infuse, actually. So it's very relevant to energy as well. In China, so Jan, if you go back to your first slide showing the whole map of China, so we do have this, yeah, so if you look at this, the water transfer currently taking place major in the eastern part of China. But this is the traditional, like, food production area in the old days. But now it's more like we're losing cropland in this area. The energy is actually on the other side, so the southwest. You see a lot of like a west routing, the other area, that area. So lots of hydro power is taking place there. So it's like a different area is in charge. So we have the food production area intensively, and then the energy hydropower production. So they are not they're not competing water from. So the water transfer is not really competing the water from the hydropower generation. And then, but we do see this imbalance within the whole country between the allocation of energy and the food production. So I think the big picture in China now is to produce more food from the northwest, because we're still holding up the fertile, very good cropland, and maybe send some of the food down to the rest of the country. And the energy area is actually intensively located in the southwest. And then some of those hydropower will be transferred to the north. So there is like a food going down and energy going up. So this is a geographical trend in China.
And do you use also energy to transfer the water from one place to the other place?
So both, I will say both. So I think a major part of the project is taking advantage of the geological, geophysical features of the place, and I think they do have some pumping facility, but it's not like heavily relying on energy to pump water from south to north.
And also for that part, it depends on the different routes. For example, in the eastern route, basically the one transfer, it depends on the existing river part. So maybe for that part, the need for additional energy will be lower, because actually for the eastern route, it's along the a river that the Chinese have been used for maybe about thousands of years. But for the central route, basically it depends on the channels that are building recently. So for that part, the demand for energy may be higher.
Yeah, I was there actually look at a project like 2-3 years ago. I think what I heard about was at the drawing point. So they do use a lot of energy to draw water to alleviate water to a very high elevation, and then so just then the water just flow down to the north using the natural the gravity.
We'll see.
Yeah, I think we still have 1 or 2 minutes for additional questions if anyone has one.
Yes.
Go ahead, please. The Chinese government spent lots of money on this, and it's like a huge project over decades. And now only this project has started to operate, I think, 5 or 6 years ago. It so far has drawn like a very controversial feedbacks. Some of them think, what's about this amount of water? The north part of China will be greatly helped. Of course, a major proportion of the water transferred will not be used for agriculture. So if you see the receiving places, they are major, the capital city and the surrounding area with high density of population and GDP. So I think part of it will be to use for civil and manufacturing, but that will alleviate. So that will alleviate the area will also have very bad groundwater depletion issues. So that will kind of protect the environmental of water withdrawal, and that's a major benefit. But along the route, so especially I think the eastern road, that was the first designed and constructed project. So it is open route, so it doesn't cover it up. So the water evaporates along the roads, and a big proportion is getting lost. And there were some also ecological issues, environmental issues, but in the middle road, it is closed up. So less evaporation and the water loss along the transportation, and less sediment issues. So I think from the engineering point of view, they are improving it. Yeah. But we hope it will be something greatly help alleviate the water deficit in the north part of China. Yeah, thank you for the questions, and thank you, Jen.
Yeah, thanks everyone.
Thank you, Jan, for your presentation. Let's move to the next presenter, who is Álvaro Calzadilla from the from the UCL, Institute for Sustainable Resources. He will present something on the role of finance and financing condition of large infrastructure projects. So the floor is yours.
Thank you very much, Martina. Do you hear me clear and do you see my presentation? Perfect. So this is basically part of a project that we have at the UCL, which is Future Dams. And in this project, which is financed by the Research Council UK, we actually aim to understand better the modeling, the governance, and also the different interactions that there are in the food, energy, water, and environmental nexus. So the co-authors of the paper are here, and it's I'm glad to see Victor and Mohammed, who are in the audience. So they will reply all the questions that we will have, and I'll go just ahead with the presentation. Sorry, something happened. Okay, yes. So basically, the aim of the paper that I'm going to present is to introduce an investment-oriented CG model that we use this to evaluate the economic impact of large infrastructure investments in developing countries, but it could also be used this in any country. And we basically consider in this framework all the phases that one of these projects has. So the construction phase, the financing phase, and also the operation phase. So we basically are, we want to assess the direct, indirect, and induced effects that this large project has. As a case study, we use the Buoy Dam, and this is what I'm going to tell in a moment. So I will just give a brief introduction of the motivation that we have. Sorry, I want to show. I cannot have access to the cursor. Okay, here it is. So I will give a brief introduction on the motivation, then I will show the main characteristics of the Buoy Dam, then I'll talk about the modeling framework that we are using, where we combine a CG model with a biophysical system model. Then I will talk about the different scenarios that we use to assess these impacts of the different financing conditions of this Buoy Dam. Then I'll talk about the results, which will explore the macroeconomic, the sectoral, and the household impacts, and then I will conclude. So basically, the achievement of the global decarbonization targets require a lot of investments in clean power generation, also in electrification of the transport sector and in low carbon technologies across all sectors in the economy. And to reach, it is estimated that an average annual investment in low carbon energy technologies and energy efficiency will need to increase by a factor of 6 by 2050 compared to the number that we have in 2015. So this is behind the 1.5 degrees scenario. And moreover, 2/3 of the world's infrastructure investment is expected to occur in the global south. So one key aspect to realize these huge investments is the access to finance. Without an external financing and relying only on internal savings, the implementation of large-scale projects in developing countries might take a very long time to be completed. And of course, there are also problems about the crowding up effects that it could have in the other areas of the economy. And at the same time, some lending in developing countries who have a low credit rating are often attached to a resource secure loans. And this is what we are going to see here in this case of the Buoy Dam. And we will see that these resource secure loans have their own economic implications. So besides the importance of the capital investments and the financing conditions, most of the work until now assess only the operation of the asset. So in this case, they assess only the electricity generation. So the emphasis they have a strong emphasis on the direct impacts, but the indirect and induced effect are almost neglected. And this is what we want to do now. When we introduce this model, we want basically a framework which allows us to assess the economic impacts along these different phases, the construction phase, the financing phase, and the operation phase, in order to assess all the impacts, the indirect, the direct, and the induced effects. As a case study, we are going to use the Buoy Dam, and the Buoy Dam is located in the Volta River Basin. So here it is the Buoy Dam, and the Volta River Basin is in West Africa, and it is geographically shared by 6 countries. The Volta River Basin has 3 main tributaries: the Black Volta, the White Volta, and the Oti River. So the construction of the Buoy Dam started in 2009 and has already been finished. And the hydro power generation was commissioned in 2013, and the power generation capacity is 400 megawatts. The Akosombo Dam, which is located here, downstream from the Buoy Dam, is the largest hydropower plant in Ghana and in the Volta River Basin. And it has a power generation capacity of 1,020 megawatts. These are the characteristics of the Buoy Dam. So we are going to divide this into the 3 main phases that we identified: the construction phase, the financing phase, and the operation phase. So, and these are the direct impacts that we have in these different phases. So in the construction phase, the project cost is $622 million US, and it has been already constructed between 2009 and 2012. And it took 4 years to build that. And of course, this has been financed in some particular way, and they use 3 methods of finance. So the first one is a $60 million US from government spending. Then they have 2 loans. One, a 20-year concessional loan of $270 million US at a 2% interest rate. The interest rate is lower than the commercial loan because it is a concessional loan. And also we have a 12-year commercial loan of $292 million US at 1.03% over commercial interest rate, which is set at 3.5%. And the interesting part of this loan, which has been with the Chinese government, is there is a collateral to the loan agreement. Basically, the Ghanaian government agrees to export up to 40,000 tons of cocoa at the world prices over 20 years. And we will see that this specific condition is the one which generates more impact in the Ghanaian economy. In the operation phase, we do have a reduction in electricity generation from Akosombo during the initial filling of the Buoy Dam, and this is basically captured by the water model that we do have here in the modeling framework. And then when we start to build the Buoy Dam, then we add the electricity generation. And then in the steady state, basically the Buoy Dam operates as in the Akosombo Dam, and the Akosombo Dam changes the electricity production due to the river flow regulation that is happening in the Buoy Dam. So these are the different operation rules regarding the electricity production in the two dams in Ghana. And here I would like to stress that we do not include any benefits of irrigation, and also we don't include any negative environmental impact, for example, losses of ecosystems and so on. And also we don't include social impacts, for example, displacement that may occur. And of course, these impacts on irrigation and environmental and social impacts are huge and are very important in order to realize and approve one of these projects. But in this study, we don't consider them. So this is the modeling framework that we use. So we basically combine a CG model, which is an investment-oriented CG model, which we call Invest CGE, which is linked to a biophysical system model. So the CGE model basically determines the macroeconomic, the sectoral, and the household level impact of this large-scale infrastructure project, in this case, the Buoy Dam. So with this framework, we can assess the construction, the financing, and the operation impacts of the dam. In the biophysical system model, we determine the hydropower generation considering a hydrological uncertainty. And then the changes in hydropower supply are then transmitted to the CG model as economic shock to the hydropower sector. And what is central here in the analysis is basically that these projects are backed by the government. So we need a specific representation of the government expenditure and the government income accounts. And also we need to consider how these different phases will impact the relationships between the government accounts with the other accounts that we have in the model. And this is basically what the investment CG model does. And the two accounts, the expenditure and the income accounts of the government, will be impacted differently at each stage of the project. In the construction phase, for example, here we can see that we can basically import inputs from the national economy and also from the rest of the world. For example, the turbines are imported from the rest of the world. And we know how much has been that cost, and that cost needs to be financed. And then there are different options for the government. One is basically, as we have seen, and this is what happened, is to just use the government income in order to finance part of it, but also it could finance by issuing bonds or getting grants and foreign loans, right? And this will be part of the general income of the government. And there is also this resource attachment, this cocoa exports linked to the loan. And then for that reason, the government needs to buy the cocoa from the farmers, and then it needs to sell this at the agreed price to China. And this is represented by these links, the resource export sales and the resource acquisition, right? And when we are in the operation phase, the government will also receive the electricity sales, and this income, this additional income, will also help to finance and to pay part of the loans that they have acquired from the rest of the world and for China. And here it is, the CG model that we use. I will just talk about some characteristics that we have. I will not go in deep. And it is based on the standard IFPRI-CG model. So it's basically a small open economy model. And we have calibrated this for 2009 to the Ghanaian economy. It's a recursive dynamic model. So we ran the model from the year in which the Buoy Dam has started the construction, 2009, and then we basically ran this until 2065. We have an endogenous labor supply because we want to know the impacts on employment. We also have a sector-specific hydropower capital, which help us to link this with the biophysical system model. And also we have a split on power generation, and we consider hydro and non-hydro power. And the main characteristics of the Invest CG model is the construction. So we have a project-specific activity which relates to the construction of the dam, and this is active only during the construction phase. So, and it reflects the real cost of the dam, as I explained, for example, the imported turbines. We also have a special financing module where we have 4 financing options, which are bonds, foreign loans, foreign grants, and the government spending. And they can include different interest periods, and also they can include different grace periods. And we have the operation phase also accounted in this framework, where the project-specific rent attributed to the project capital are separated from other rents. In this case, basically, the rents of this capital is the electricity which is generated by the Buoy Dam. As you can see, so we have introduced in the model several characteristics which allow us to assess these different phases of these infrastructure projects. I'll talk now a little bit about the biophysical system model. So it's a simplified, monthly engineered system model developed for the Volta River. It estimates electricity generation from the Buoy Dam and also the impacts that it could have on generation on the Akosombo Dam. So the model covers a period of 1993 to 2013, and it includes 3 inflow points. So basically the main 3 tributaries that the Volta River has, that I show in the previous slide. And the model was calibrated from 1993 to 2003 and was validated from 2004 to 2013. And there are 2 operating rules for the 2 dams that I explained in the previous slide, so I will skip this part. But what is important is also that the hydrological uncertainty was generated considering 50 possible hydrological futures sampling historical river flow records. So we have run 50 simulations also in the CG model. And those are the scenarios that we have. So we have 2 groups of scenarios. One is without the Buoy Dam, and the other one is with the Buoy Dam. And both group of scenarios include population and labor supply changes based on the SSP2 and also an endogenous capital accumulation. Both scenarios include hydrological conditions, historical hydrological conditions for the period 2009-2016, because we do have the data, but we include 50 stochastic hydrological conditions for the period 2017 to 2067, so 50 years, assuming historical variability. So we don't consider any impact of climate change in these simulations. As a baseline scenario, we use the scenario in which the electricity generation is only from the Akosombo Dam. So there is no Buoy Dam in our baseline scenario. In the other 3 scenarios, we consider generation from the Akosombo Dam and also from the Buoy Dam. In the electricity only scenario, we increase the hydropower production without considering investment and finance needs. So basically, this is just looking at the operation of the dam. So it replicates previous impact assessment, which consider only the operational stage. In the second scenario, loans, we include in addition the construction phase of the dam and the 2 government-backed loans, only the repayment of these loans. In the third scenario, loans plus exports, we include in addition the cocoa exports over the period 2010-2028. And basically every year we export, the model exports 22,000 tons of cocoa, which is equivalent to 2.8% of the total production in the calibration year. So those are the 3 scenarios that we are going to evaluate. And here we do have the results. In this part of this slide, you can see the different periods that we have for the different phases of the Buoy Dam. So we have the construction period, we have the filling period, we have the electricity generation period, we have the period of the two loans, and also we have the cocoa exports. Right, as you can see, there is a lot of things going on in the Buoy Dam, and every of these has an impact, an economic impact, which will basically determine the GDP and the sectoral impacts. As I said, most of the analysis only focus on the electricity generation, but we want to make a case in order to include as well the construction and the financing sectors and the special loan conditions that we can have. So in the electricity only scenario, here you can see the GDP, employment, general investment, and exchange rates. These are basically changes from the baseline. And we do have three scenarios: electricity only, loans, and loans plus exports. So in the electricity only scenario, the red lines, GDP is expected to increase by 0.18% in the filling period, and then in the long term by 0.55%. So it's a very small increase, but basically the increase in hydropower generation have a positive impact in the other sectors, which will also increase employment and will increase investment. In the loan scenario, the GDP declines during the construction phase, as we can see here, by very small amount, and this is mainly due to two reasons: the crowding out effect of labor and capital, and the higher investment cost outside the dam construction. And during the operation phase, the repayment of the loans induce a depreciation, as we can see here in the green line, of the domestic currency, and this stimulates exports and economic growth. And for this reason, it's a little bit higher, the growth in this scenario. In the loan export scenario, here we can see that the export of cocoa to China generates a huge increase in GDP in the period 2010 to 2018, mainly because of this cocoa exports agreement. And also this leads to an increase in the investment. And because of the cocoa export leads an appreciation of the local currency, affecting negatively other exports. However, the net effect for most economic sectors is still positive in the long run, and this is why we can see a positive impact on GDP. In this graph, we can see the sectoral impacts. In the electricity only scenario, we will have a positive impacts in all the sectors, and this is substantial in the industry and other services which use a lot of electricity. And also we can see that the non-hydropower and other energy is negatively affected because of the substitution effects. In the construction phase, for the loans scenario, we can see that most of the economic activities have a slight decrease in output because of the crowding out effect that I mentioned about labor and capital, with the only exception, the construction sector, because now as we are considering the construction sector, then this activity will increase the output and it will be around 1%. And here we have the impacts on the repayment phase. So we can see here that the public service are differently affected than the private sector. We have a decline in the public services, and this is because the government needs to pay the difference between the sales of electricity and the loan repayments. And the loan repayments in foreign currency increase the exchange rate. Therefore, all other activities show an increase in output compared to the electricity only scenario. And finally, in the loans plus export scenario, agricultural production increases a lot because of the cocoa exports, but also higher prices for agricultural commodities are expected as land availability declines and land rents increases. And for that reason, we can see that the agri-food sector is negatively affected, and this is also happening in the industry sector. And the government spending, on the other side, declines by around 1%. And this is because the government has to compensate the cocoa export and the cocoa producers because of the difference in the world price and the domestic price. As I don't have that much time, I will just skip this graph. And I want to mention that in this graph, we have the cumulative impacts between 2009 and 2065. So in the whole simulation period, and we use a 10% discount rate. So here we can see that the mean cumulative impacts in all scenarios are above the initial value of the project, which is 622 million US dollars, which is basically represented by this red line. So we can see that in any case, in any of the scenarios that we have considered, there is a positive impact of the Buoy Dam. But we can see this is what the majority of the analysis of the papers do. They only consider the operation case. But if we consider the financing and the construction phase, then we know that the impacts on GDP increases by 68%. So it is really important to consider these different phases of, related also to the construction of these infrastructure projects. And we can see that in general, there is the rural households gain more than the urban households, and they gain even a larger quantity when they are basically exporting cocoa to China. And here I have the conclusions. So basically what we have done is to introduce this Invest CG model, which accounts for the construction, financing, and operation phases. And we have seen that this very important to include these aspects, because as we have seen, the Buoy Dam leads to a 68% increase in the mean discounted GDP compared to the electricity only scenario when we assess the loan and export scenario. So basically considering all the different phases of the project. So basically what we want to do is to support the claiming on the literature that the economy-wide approach needs to go beyond the quantification of the direct impacts only. So we need to consider the indirect and the induced impacts in the construction, in the financing, and in the operation phases of this infrastructure project. Thank you very much.
Thank you, Alvaro, for your presentation. Real interesting piece of work, and I'm rather impressed for all the work you have done. So from the audience, any questions?
Let me ask one question. Maybe I'm having some others. So at the end, Alvaro, you were talking about the impact to the rural household is higher than the urban household.
Yes.
So I was wondering, so you mentioned about the cocoa production, so, and then that may have an impact on land availability and maybe drive up land rents. So why the rural got more benefit from that? Because the land rents are higher, or because the exporting cocoa give them specialized benefits, profits?
Yes, basically the rural households, they work more on the agricultural sector, and the agricultural sector experience a boost in production because of these cocoa exports, right? It's basically that they are exporting more than they were doing before. And for this reason, the rural households who work or who basically own the land, they profit from this situation. And for that reason, the income and the expenditure of the rural households increases. And we can see here that the increase is very evident when we contrast this with the income of the rural households in this scenario, where we include the cocoa exports to China.
But do you consider the commodity price changes? Like yes. I think the contracted price probably likely will be less volatile than the actual market price.
I mean, you mean that the difference in price of the cocoa at the domestic price and the cocoa at the world price?
I think when they export, they sign the contract for 20 years exporting to China, probably under some contracted prices. So that is probably fixed or relatively stabilized than the market price.
Yes, that's right. I mean, the difference on the GDP and also mainly the difference in the public income and expenditure will depend a lot on the level of prices of the cocoa in the domestic price and the cocoa in the world market price. What we have seen here is that the government has to basically subsidize that price. So basically the government buys cocoa from the local farmers and needs to sell this as a price which is below what they expected. So there are basically financing these sales, but of course this was part of the agreement of the loan, right? And this is kind of a fixed world price which will basically help the Ghana government of having this loan, and also for the Chinese government is like a fixed supply of resources at an agreed price, which will be a little bit beneficial for them as well.
Yeah, that makes sense. Thank you.
Can I ask a follow-up question to that?
Yep.
Of course, please.
Yes, many thanks for the great talk. And now we talk about cocoa, not about hydro. But I have a question about cocoa as well, because that 40,000 tons is roughly 5% of Ghana's annual production, if I'm not mistaken. And to what extent does this, lead to an increase in production? To what extent is it just a substitution of existing exports? Because I'm not really clear on how that is really stimulating the agriculture sector. Maybe I've missed that in the presentation.
Yeah, basically, the agreement is that Ghana has to export up to 40,000 tons of cocoa. But in our simulations, we have seen in Comtrade that the exports are around 22,000 tons of cocoa. So we use this number in order to basically increase the exports to China. Of course, there are some substitution possibilities, but in general, what we observe in the agricultural sector is that there is a higher demand for cocoa. And this is basically leading of all these changes in a higher production of agricultural output, and also a higher income for rural households which work on the agricultural sector. I don't know if that replies your question.
Yeah, thank you. Thank you.
Other questions? Well, I have one myself. Yeah, please go on. Please go on.
Should I go on or should Martina go on?
No. Please go on.
Oh, okay. On this slide, you show that labor supply changes are based on SSP2, and earlier you said it's endogenous based on the wage. Is that? I'm just confused by that.
No, we introduced a labor supply curve, but this. So what is endogenous is the capital accumulation here, and basically. Sorry?
Well, just that, because you could give the detail exactly. So,
okay.
Basically, the endogenous labor supply gravitates around some kind of a baseline value, right? So you have a reference supply when the price is 1, and then depending on how the wages go, have an increase or decrease in supply. And what we actually change with the SSP2 is to change that reference value across a number of years. So you have an overall effect of an increase in labor supply, but you also have this effect of endogenization based on changes in wages.
Okay, thanks.
What I can see is like the labor supply will move according to the SSP scenario that we are using, right, Victor?
Exactly, yeah.
Mm-hmm.
Okay.
Okay, quick question for you, Alvaro. How did you treat in the model the closure, the foreign trade closure? So the rest of the world closure, because if you have foreign loans, I saw the exchange rate varies. So how did you treat? I am just curious.
Yes, exactly. I mean, I can go first and then Victor, if he can as well. So basically what we have done is because we do know how much are the loans. So basically we treated the foreign savings as exogenous. And this implies that the exchange rate needs to be endogenous, needs to be free to adjust. And that's for that reason that we do have these appreciations or depreciations of the local currency. When we are, for example, if we are paying the loans, then we are basically bringing out US dollars from the Ghanaian economy to the rest of the world, and then the interest rate will adjust in order to bring the foreign savings to the exogenous level, which is fixed in the model, right? And that's the adjustment mechanisms that we have. So foreign savings is fixed, and the exchange rate is endogenous, is mobile.
Okay, thanks a lot for the clarification. So are there any other questions? Okay, so we should have now the third presenter, but he didn't show up. And the fourth one, who is Khalid, cannot reach us in short time because he's busy with some classes. So we should wait for Khalid. I would suggest to leave the session open and just wait for Khalid joining us. What do you think, Jean?
Yes, I will suggest the same thing in case people are interested in Khalid's presentation will miss it. And so I think I will pause here until 10:05. So the final presentation, according to the schedule, is supposed to start on 10:09. So let's come back on 10:05, try to see if we can get connected with Khalid.
Okay, fine. So see you later.
Yep.
Thank you.
Thank you all. Thank you all for attending.
Yeah, excellent talks.
And to the presenter. Yeah, for the moment.
Great.
Okay, so Jean, see you later, right? You are muted.
Yeah, I will keep the room open, but feel free to wander around and remember to come back around 10 or 10:05.
Okay, so it means in 20 minutes, more or less.
Yes.
Okay,
Yes, exactly.
see you later.
See you. Looks like we have 1 minute to go, and I haven't seen Khalid showing up, right?
Yeah. I don't see Khalid, so I don't know.
He just reached out to me. He's having issues accessing the website of the conference.
Oh, very good.
Very
good.
But yes, that's true. I think Ginger has sent us an email like Purdue is having problems with the WebEx. So let me here. I think if he doesn't have the access to the link, I'm posting it to the chat box right now. So anyone can, so who can reach out to Khalid? Could you please send this link to him?
Okay, I'll copy that.
Okay, thanks a lot.
Thank you so much. Yeah.
No problem.
Yeah, I don't know why Purdue website is collapsing. Yeah, let's wait a couple of minutes to see if Khalid can join us successfully. Mohammed, are you getting any replies from Khalid?
Yeah, I sent him the link. I think he's still trying to join.
Okay.
How much transition time there is between this session and the next slot?
So the next track, I believe, will start at 11 o'clock sharp. So depending on when Khalid can join us successfully, and then
yeah, he said he's still the WebEx is still loading, so he's trying to join. But he suggested that maybe I can start by giving the introduction part of the presentation, and then when he joins, he can carry on.
Yeah, sure. If you have the slides, that would be great.
Yeah, it would be good. It would be very good to have you started.
All right.
Okay, so shall we proceed this way?
I think so. Yeah.
Okay, so well, welcome back. And the last presentation will be about the economy-wide assessment of the impacts of Nile sediment reduction on the Sudanese construction sector. The presentation will be introduced by Mohamed Bashir, and then once Khalid joins, he will keep with the presentation. Thanks a lot. Mohamed, the floor is yours.
Thank you very much. Let me start sharing my screen. Can you see my screen now?
Yes.
Yeah, perfect. Yeah, thank you very much for having us today. So we've been doing some work looking at some impacts of damming the Nile on other secondary sectors that are not conventionally considered in impact assessments of dams. So the title of our presentation is Economy-Wide Assessment of the Impacts of Nile Sediment Reduction on the Sudanese Construction Sector. Here we're looking at the impacts of one of the most controversial infrastructure projects that are being built now on the Nile. It's called the Grand Ethiopian Renaissance Dam. It's here on this map, the greenish triangle here. So it's under construction in Ethiopia, around 15 kilometers upstream of the Ethiopian-Sudanese border. And the construction started in 2011 and is still going on. And the initial filling of the dam actually started last year. So this dam has been creating a lot of political tension between Ethiopia, Sudan, and Egypt on the operation and filling of the dam of the reservoir. The reservoir has a capacity of 74 kilometer cube or billion cubic meter. So that's equivalent to 1.5 times the average annual flow of this river. So if this river is to be filled in as fast as possible, it will take 1.5 years on average. So it's quite a large dam, and it's going to change the flow pattern, the river flow pattern downstream of the dam to Sudan. As I said, this dam triggered much tension, mainly on the impacts on hydropower generation downstream. So there are a couple of dams in the downstream, as you can see here in Sudan, the black triangles, and there is the High Aswan Dam, which is in Egypt, And there's also the impacts on the dam on irrigated agriculture in the downstream. So these have been the main highlights of the negotiations. It's quite known now in the literature that this dam, when it's built, because the purpose of the dam is hydropower production, is going to change the flow pattern. So instead of having variable flow with most of the flow happening during the flood season, it's going to regulate the river flow to Sudan. And Sudan is going to benefit from that in terms of irrigated agriculture and hydropower generation. This has been shown by previous studies. But this flow regulation effect, on the other hand, will also have negative impacts on Sudan in terms of environmental impacts, and it's known that intervention in natural systems by building dams will have impacts on fish and ecosystems and so on, and will also result in a loss of recession agriculture, because when you regulate the river flow, then you lose the natural floodplains. Again, also the long-term operation of this dam is expected to reduce hydropower generation in Egypt from the high Aswan Dam, and also could result in water deficits in Egypt, especially during times of multi-year droughts, because water can be held upstream, which results in a drop in water storage in the downstream. Now, also the Blue Nile, on which this dam is being constructed, is known to carry very large loads of sediment. So on average, it's estimated that it carries between 111 and 140 million tons of sediment per year. But once this dam, the GERD, is built next to the Ethiopian-Sudanese border, it's estimated that around 86% of this sediment is going to be trapped in the reservoir of the dam. And that has a few implications, but few of them are positive and some of them are negative. On the positive side, this reduction of sediment is going to increase the lifetime of the reservoirs in the downstream, because if you have less sedimentation in downstream reservoirs, that means they can be operated for a longer duration. But that also reduction in sediment will reduce the cost of maintaining irrigation canals and pumping stations and so on. But on the other hand, this sediment is actually a source of livelihood for quite a few Sudanese in the downstream, because it provides fertility, natural fertility for agricultural lands. So this will need to be replaced by fertilizers, and then there are all kinds of health issues associated with that. And then there's also the impact on the production of fired clay brick production, and this is actually the main focus of this talk. So in Sudan, there are industries that produce bricks for the construction sector, and that brick is based on the sediment that is carried every year to the floodplains, and then these sediments are dug every year and converted into fired red bricks. So once the sediment is trapped in the upstream, there will not be any fired red brick production in the downstream any longer. So in this study, we are attempting to quantify the economy-wide impacts of the GERD on Sudan as a result of this anticipated reduction of fired clay brick production, because the sediment will be reduced. Now, in our approach, we relied on some statistics from previous studies on how much of the brick production in Sudan is going to be impacted by the GERD, because the GERD is just going to impact, if we go back to that map, the GERD will impact the production of bricks along the Blue Nile here and then along the main Nile. But there's red brick production elsewhere in the country that will not be impacted by this dam. So first, we needed to quantify the magnitude of red brick production that will go out of the Sudanese economy, and then we also needed to put together a social accounting matrix that accounts for this sector, which is brick production. So we conducted a structured survey with construction engineers in Sudan, with 32 engineers who contributed to the design and construction of over 500 buildings in Sudan over the past 10 years. And we asked them specific questions so that we can create this new sector, taking it out of the construction sector of Sudan. So we asked them about the share of buildings that use fired fire red bricks, and because there are other kinds of bricks that are also used for the construction, we also asked them about the share of the cost of bricks normally in the construction of buildings, and the cost of this component. And then based on that social accounting matrix, we developed a CGE model for Sudan, and that includes a red brick production sector. Now, is Khalid here yet? Because I would prefer if he were here to talk about this part. Not yet. Okay. Okay, so I'll try to carry on, and perhaps he can add to what I say later on. So after we kind of created that new sector, so we looked at the structure of the economy based on that sector. So here, this graph on the right-hand side shows the cost structure of this new sector, and we can see that this sector relies on male semi-skilled labor. That's most of its production cost goes into labor, but it also relies on other factors such as biofuel and petroleum for pumping some water from the river, and cattle. So by cattle here we mean the manure of cattle that is used to fire the red brick production. Then, if we look at the demand for the clay red brick commodity, we can see that most of it is used by the investment, and the second highest user is the building and construction sector. So these are the sectors that are going to be impacted the most by the reduction in fired red brick. Now, we had to look at also the structure of where where red brick is produced in Sudan. So as I said earlier, there is a production on the Blue Nile and the Main Nile. That's what's going to be impacted by this new dam. And we can see that actually most of the production of fired red brick in Sudan is based on the Blue Nile and the Main Nile. So in total, it's around 92% of the production of red brick. So this is going to mostly disappear after the construction of this new dam. So that's basically our shock to the economy by reducing 92% of fired red brick production. Now let's move on to the next slide. So here, so one of the sectors that's going to be impacted largely by the reduction in fired red brick is the construction sector. And we can see that in the production structure, in the intermediate demand structure of that sector, 20% of the intermediate demand comes from the red brick industry. So that's going to have a large impact on the construction sector. Now, if you look at how this new dam, the Grand Ethiopian Renaissance Dam, is going to impact the Blue Nile flow, we can see that. So these are a few gauging locations along the Blue Nile and the Main Nile, and we can see that without that dam, the river was highly variable with a high peak during the flood season every year. But with that dam, it's upstream. We'll have this regulation effect, which of course is going to prevent the river from flooding to the floodplains. And again, also as I mentioned earlier, also this dam is going to reduce the sediment load, resulting in the elimination of the red brick production along the Blue Nile and the Main Nile. Now, we formulated two scenarios. One we call it conservative scenario, and another one we call it gradual decline scenario. So in the conservative scenario, we assume that the reduction of the 92% in the production of red bricks in Sudan occurs in 1925. So that's following the initial filling period of the dam, because once you build a dam, you need to fill it first, and then you start using it. So we assume that the filling period is not going to have any impact on the production of fired red brick. But in the other scenario, we assume the gradual decline leading to a total of 92% by 2025. So we would be expecting a higher impact with this gradual decline than a conservative impact, because here we have the impact of these initial years. Now, we implemented these shocks on the land demand of the red brick production sector, because once you go out of once this sector, once a certain proportion of this sector goes out of production, that means it doesn't use that land any longer for the production of fired red brick. So we applied the shock to the land demand of this of the brick sector. So if there's a 92% decline in the sediment, or 92% decline in the production of that sector, we simply reduce land by the same proportion. Now, if we look at some results, so this plot here on the left side shows the two scenarios. So this shows land demand demanded by the fired red brick production. So in the baseline, there is a gradual increase in land, but in the two scenarios, we bring down the land component to the proportion of the shock of the respective scenario. So you've got a gradual and then a sudden shock in 1925. Now, if we look at the contribution of this sector to GDP, we can see that the contribution of the sector declines slightly. I mean, if we look at it like that, but there is a decline in the yellowish line and the red line. They are lower than the baseline, so that's a reduction in the GDP contribution of the clay red brick production sector. Now, if you look at other impacts, so here, if we look at the change in GDP, so this is the difference between the two scenarios and the baseline, we can see how the two scenarios are impacted by the shocks we applied. But we can see also that these shocks propagate to other sectors, like the construction sector, where also the GDP contribution of the construction declines over the years, and other secondary sectors like real estate, which relies on the construction sector, and the trade sector, which also has some dependence on both the brick production sector and the construction sector. Also, we looked at some of the impacts of households, and here we can see that households are going to be impacted, and the household that will be impacted the most in this case is the urban households. I can see that Hali is already online. Can you hear us?
You carry on, Muhammad. You are doing a very good job.
Oh, thank you. Yeah, I haven't realized you were here. Okay, so yeah, so urban household number 5 is going to be impacted the most, and and then if we look at the so the impact in total on all our households together, so we can see there's up to $5.17 billion over the years. This is assuming that there's no kind of intervention to help alleviate the impact of this reduction in fired red brick production. Finally, if we look at some macroeconomic impacts, we can see that there is this is the percentage change in GDP and agriculture GDP and service GDP, industry GDP. So overall, there is around 0.23% change in overall GDP in the gradual scenario compared to 0.21% change in the conservative scenario. We can also see that these impacts are in the other sectors, but overall on GDP between 6.23 and 6.94 billion dollars over 20 years, over 30 years between 2020 and 2050. This is accumulated impacts without any discounting. Again, I want to stress that these impacts do not consider any measures, as I will talk about in a bit. So in the conclusions here, so we've seen that the GERD will have impact on the hydrology of the river by reducing the sediment load and by regulating the river flows. And this reduction will have macroeconomic impacts and distributional impacts on Sudan in terms of on the construction sector, on the production of fired red brick. So far, the transboundary negotiations between Ethiopia, Sudan, and Egypt on GERD management has focused on hydropower generation, irrigation, water supply, but there hasn't been much attention to the environmental impacts and indeed the secondary impacts on other sectors, such as the fired red brick. So these sectors need to be considered in these transboundary negotiations. Yeah, but again, it's also worth mentioning that any reduction in fired red brick would have positive environmental impacts because it reduces the cutting down of forests. Because that industry uses wood to fire the bricks, and then it would also reduce greenhouse gas emissions from the firing process. Lastly, in this analysis, as I mentioned earlier, we don't consider the growth of other industries that produce bricks. So here we're simply assuming that the economy will have to deal with this reduction without any replacement for that for the fired red bricks. So in future work, we're planning to add other the production of other brick industries. For example, there is cement-based bricks that can replace fired red bricks, but this will obviously require investment and will have also economy-wide implications. And also, government can help reduce the impacts on households by providing financial and technical support to transform the use of floodplains from the production of bricks to other activities. And alternative activities for using floodplains could be irrigation, agriculture, or recreation. And as I said, other brick production activities could be also if supported, could help compensate for the reduction in red brick production. Yeah, these are all the slides I have. Perhaps Khalid might have a better version of the slides. Yeah, but thank you very much for your attention.
Dr. Mohammed, thanks a lot. Presentation on behalf of Project. I think he's smiling, so he's really satisfied with your presentation. So any comments, questions? Please.
I guess one question for Dr. Khalid. Hi, Khalid. I'm just wondering from where you get the SAM. I mean, you mentioned the data use social accounting metric for Sudan. What's the source of that SAM? Because as we know, the Sudan does not publish input-output tables, official input-output table. Just wondering about where you get this data, and I need you, if you have time, to detail the CD model you use. Thank you.
All right. Yeah, go ahead, Mohammed. Or?
No, I think you should take this questions from now. Yeah.
All right. Thank you very much. First of all, I would like to apologize for the technical issues that I faced here, and my greetings to Ying and Martina for your patience. Very, very much. I appreciate that. Yes, and thank you very much for the question, Al-Amir. The Sudan do not produce officially input-output tables, but we have been in close, I can say collaboration and communication with the statistical office, and we know what kind of data is available there, and we do our best to produce kind of economy-wide databases out of it. The latest input-output table produced by the statistical office officially was from 1961, but since 15 years, I have been working with data on Sudan, and we know that the data has some issues, but I think for now the social accounting matrix we have a social accounting matrix published, available online, with more information on the documentation on the data sources and the processing that we usually do. You can access it. For the work on this data, for this particular data set, it is not published yet, but we are working on a version that can be published. If you are interested in working with Data on Sudan, maybe you simply stay in touch with me, and we can see options to help. And I'm not sure if Martina would like me to talk about the CG model as the person asked. Maybe if we have time at the end, I can talk about it in details.
Well, we can first answer to Jonas. He has a question in the chat. So Jonas, you can show up if you want and just ask the question directly to Khalid.
Yeah, thanks. Okay. I was just wondering about the total effects of the dam. You were presenting now on the negative impacts you see for the brick production, but we have also the positive impacts due to the irrigated agriculture and electricity generation. So how does it weigh? I mean, would they be overweighing those negative impacts here?
Okay. Yeah. I know from where Jonas is coming. Otherwise, I would have said Jonas has some, political objectives behind this question, because this dam is getting really sensitive. And in all the presentations about it, you need to list all the positive impacts and all the negative impacts, and then you highlight which one of them are you talking about. And as Jonas rightly mentioned, there are many positive impacts of this dam. We have studies addressing that. Muhammad has published a lot on this. But here we are only focusing on the sediment reduction that is channeled in the production of fired clay production, fired clay brick. So we assume that everything else is constant. But of course, there are many other impacts that are not included here, and Muhammad has listed some of them in the conclusion, and in the written article there will be more elaboration on that. Muhammad, would you like to add to this?
Yeah. Maybe just, I mean, in general, yeah, dams have positive and negative impacts, and normally the positive impacts are easier to quantify, because if you look at irrigation and hydropower, these are easily measured, and there are models that can, with a long history of quantifying these impacts. So what we're trying to do here is really to look at this dark area where nobody looked at before, and try to come up with these numbers, and hopefully this will help, make a good decision by looking at both the positives and the negatives.
Can I have a question, Martina?
Of course. Please go ahead.
Yeah, thanks. Khalid and Mohammed, thanks a lot for this very interesting talk. You mentioned that the Blue Nile makes up either 82 or 92% of the sediments needed for the brick production, and the other rivers only provide a small share. I'm wondering, are these other rivers already at their maximum, or could you still, exploit or extract more sediments from those other rivers in order to offset a little bit this very strong reduction in the sediment availability?
Should I go, Mohammed? Thank you very much, Ant. This is a very nice question, and nice to meet you all guys here. Thank you for being in this session. Yes, I think technically this is an interesting question, because this is actually one of the plans that we have while revising the paper, to separate the rest of the brick production into a separate sector. Now, what we're doing is that we're assuming that all the brick production is produced by this sector, and this sector would be reduced by all the share that is coming from the Blue Nile and from the main Nile. I mean, so this is the brick that is produced on the banks of the Blue Nile and the main Nile after meeting the Blue Nile, after the merging between the Blue and White Nile. So the rest of the brick that is produced, which is less than 10%, is now still in this sector, and therefore when we run these simulations, the adaptability and the positive implication on the presumably the other type of brick production sectors is dumped, because it is tied to this sector. But when we separate that in another sector, you would see the two sectors producing one commodity, maybe with somehow relaxed aggregation elasticity between the two, one could allow the other part, the other fraction of the brick production sector to flourish. It will be small, but then in a dynamic settings with somehow longer perspective, one would see that sector somehow capturing some of the investments and somehow dampening the overall impact. I hope I understood exactly what you are heading, because that is a corner which we are looking at right now.
Yeah, I think maybe also I misunderstood. Mohammed showed this nice graph of the different rivers merging. I think then probably what I overlooked is that it merges into one big river, and then you only have this one big river and coming into Sudan. And well, I guess there will be some uncertainty related to how much is still available, and I guess maybe it would be nice to do like a stochastic or simple sensitivity analysis. Right? I mean, instead of using 1 point estimate of a 90% reduction, maybe a little bit more positive or even more pessimistic view on how much will be available. I think that was my main point. But yeah, I guess you still have lots of plans to take this further. So yeah, I'm looking forward to your next presentation.
Thank you. Maybe Mohammed, you would like to add something on this, or?
Yeah, I can add here. So the river on which this dam is being built, the Blue Nile, actually carries most of the sediment load that comes into Sudan. The White Nile, which actually starts from the Equatorial Lakes area, it goes through a very famous swamp area in South Sudan called the Sud, where most of the sediment actually settles there. So that river is relatively clear. It doesn't carry much sediment. Most of the sediment comes from the Blue Nile, and once the GERD is built, then you've got a huge reduction in the sediment load. So the 92% number that we showed, that is not the sediment load of the river, but rather that is the percentage of brick production industries that are based on the rivers that will be impacted by this new dam. So basically what we're saying here is 92% of the industries that are based on the Blue Nile and the White Nile, 92% from the total of Sudan is going to disappear. So that's a shock.
All right, thanks.
I have a follow-up, if I may.
Yes, of course.
So yeah, I was just wondering. I mean, now that the GERD is being built, I mean the sediment is not away, right? I mean, it's probably caught, caught by the dam, but they need to flush it, right, from time to time. Or what is happening basically with the sediment? Will that then be used in the Ethiopian brick industry, or is it still maybe due to this flushing exercise be transported through the Sudan? Any ideas on that?
This is a Mohammed question. Go ahead, Mohammed.
All right, I'll take that one. So so the GERD is one type of dams called multi-year storage dams. So there is there's another type called seasonal storage, and seasonal storage dams, these are the ones that are normally flushed every season. These are the ones like the ones in Sudan. So these are flushed every season to take away the sediment. But multi-year storage dams, they are not flushed. They keep storage over many years, and they are never flushed. So what happens is they're designed them so large, such that they have a long lifetime, so they don't fill up with sediment very quickly. And your other question about where that sediment will go, it will just stay at the bottom of the reservoir. No one will be able to reach it because it's down there.
Okay, I think that we should stop here in order to let people go to the next session. And thanks to all for attending, especially to presenters. And okay, see you in one next slot, probably. And have a good rest of the GTAP day.
Yeah.
Thanks.
Yeah.
Bye.
Thank you.
Thank you very much.
Bye.
Thank you very much.
Thank you.
Bye bye.